How can we integrate native peoples' variety of regenerative agriculture systems into modern society to increase sustainability and environmental friendliness globally? Integrating indigenous regenerative agriculture into modern society is one of the most promising ways to improve sustainability, strengthen food security, restore ecosystems, and adapt to climate change. Indigenous communities around the world developed sophisticated agricultural systems over thousands of years by observing local ecosystems and working with natural cycles rather than trying to dominate them. The goal should not be to simply borrow techniques. Instead, modern societies can build partnerships with indigenous communities, respect indigenous rights and knowledge systems, and adapt these approaches to local ecological conditions. Why indigenous systems matter. Many industrial agricultural systems prioritize maximizing short-term yields through monocultures, heavy tillage, synthetic fertilizers, pesticides, and large-scale land conversion. While productive, these methods have contributed to soil degradation, biodiversity loss, water pollution, deforestation, greenhouse gas emissions, increased vulnerability to drought and pests. By contrast, indigenous regenerative systems often emphasize diversity instead of monoculture, long-term stewardship, soil regeneration, water conservation, integration of people within ecosystems, resilience to environmental variability. Many of these principles align closely with modern fields such as agroecology and regenerative agriculture. Indigenous systems that could be expanded globally. The Three Sisters System. Developed by numerous indigenous peoples of North America, the Three Sisters System grows maize, beans, squash together in complementary relationships. Benefits include beans fix nitrogen into the soil, corn provides structural support, squash shades the soil, reducing weeds and evaporation. Multiple crops reduce pest outbreaks. Nutritional diversity improves diets. Modern applications include urban community gardens, smallholder farms, school gardens, intercropping systems on commercial farms, indigenous agroforestry. Many indigenous societies develop forest-based food systems. Examples include indigenous communities in the Amazon basin cultivating diverse forest gardens, traditional home gardens in tropical regions, shade-grown systems for cacao and coffee. These systems combine trees, crops, medicinal plants, pollinator habitats, sometimes livestock. Modern integration could involve replacing monoculture plantations with agroforestry, incentivizing farmers to plant native trees, designing cities with edible landscapes, including agroforestry and agricultural subsidies. Benefits include carbon storage, biodiversity conservation, and diversified income. Terraced farming. The indigenous peoples of the Andes, including ancestors of the Inca, developed sophisticated terrace systems. Advantages include reduced soil erosion, better water retention, expanded cultivation on steep slopes, microclimate regulation, improved drought resilience. Modern uses include restoring degraded hillsides and protecting mountain agriculture from climate impacts. Cultural burning. Many indigenous peoples used carefully managed low-intensity fires. Examples include practices among indigenous communities in Australia, native nations across Western North America. Benefits include reducing catastrophic wildfire risk, recycling nutrients, supporting wildlife habitat, encouraging growth of useful plants, maintaining ecosystem diversity. Modern integration could include partnerships between indigenous fire practitioners and government agencies managing forests. Water harvesting systems. Indigenous communities develop sophisticated approaches to managing scarce water. Examples include desert runoff harvesting, floodplain agriculture, seasonal wetland cultivation, traditional irrigation canals. These systems often work with natural hydrology instead of replacing it. Modern adaptation could improve resilience in drought-prone regions experiencing climate change. Policy changes needed. Successful integration requires more than adopting techniques. Respect indigenous rights. Governments should recognize indigenous land rights, protect traditional territories, ensure free, prior, and informed consent, share benefits arising from indigenous knowledge, reform agricultural subsidies. Many subsidies currently favor monocultures. Policies could instead reward soil carbon improvement, biodiversity enhancement, agroforestry adoption, water conservation, regenerative practices. Support indigenous leadership. Indigenous people should be partners and leaders, not merely sources of information. This means funding indigenous-led research, including indigenous experts in policy development, supporting community-led restoration projects, creating equitable intellectual property arrangements. Education and research. Universities and agricultural institutions could integrate indigenous ecological knowledge into curricula, develop participatory research with indigenous communities, compare indigenous and conventional practices scientifically, train farmers in place-based ecological management. Combining indigenous knowledge with modern tools such as satellite monitoring, precision agriculture, soil testing, and climate forecasting can create powerful hybrid systems. Urban applications. Cities can also benefit by creating community food forests, rain gardens, native pollinator habitats, school teaching gardens, composting programs, edible public landscapes. These initiatives reconnect people with local ecosystems and food production. Challenges. Some barriers include scaling practices appropriately, avoiding cultural appropriation, adapting techniques to different ecosystems, economic pressures favoring industrial production, limited policy support, loss of indigenous languages and knowledge due to historical displacement. Addressing these challenges requires collaboration, humility, and long-term investment. A global vision. Integrating indigenous regenerative agriculture does not mean abandoning modern science. Instead, it means combining the strengths of both systems: indigenous ecological wisdom developed through centuries of observation, modern scientific understanding, appropriate technology, and supportive public policy. By shifting from an extractive model of agriculture toward one based on stewardship, diversity, reciprocity, and regeneration, societies can produce food while restoring soils, conserving biodiversity, strengthening communities, and reducing humanity's environmental footprint. Indigenous peoples around the world have developed agricultural systems through centuries and often millennia of careful observation, experimentation, and adaptation to local environments. These systems were not primitive versions of modern agriculture. Many were highly sophisticated approaches designed to sustain communities over very long periods while maintaining the health of soils, forests, grasslands, rivers, and wildlife. In many places, these systems supported large populations without causing widespread environmental degradation. Modern society faces enormous challenges related to climate change, biodiversity loss, soil depletion, water scarcity, pollution, and food insecurity. Industrial agriculture has increased food production dramatically, but it has often relied on practices that degrade ecosystems over time. Integrating indigenous regenerative agricultural systems into contemporary societies offers an opportunity to combine traditional ecological knowledge with modern scientific understanding and technology to create food systems that are productive, resilient, and environmentally sustainable. Understanding indigenous regenerative agriculture. Regenerative agriculture refers to farming practices that improve ecosystem health rather than simply minimizing harm. Indigenous regenerative agriculture goes beyond a set of techniques. It reflects a worldview in which humans are participants within ecosystems rather than separate from them. Many indigenous cultures emphasize principles such as reciprocity between people and nature, responsibility to future generations, observation of ecological patterns, diversity as a source of resilience, harvesting without exhausting resources, adaptive management based on changing conditions. These principles often contrast with industrial models that emphasize maximizing short-term output and efficiency through specialization and standardization. For example, many industrial systems focus on producing a single crop across thousands of acres. While this can increase efficiency, it often creates vulnerability to pests, diseases, droughts, and market fluctuations. Indigenous systems frequently spread risks by cultivating diverse species that support one another ecologically. The Three Sisters system. One of the most widely recognized indigenous agricultural systems in North America is the Three Sisters method, practiced by numerous indigenous nations including the Haudenosaunee Confederacy. The system involves planting 3 crops together: maize, beans, squash. Each crop performs a different ecological function. The maize grows tall and serves as a natural support structure for climbing beans. The beans host nitrogen-fixing bacteria on their roots. These microorganisms convert atmospheric nitrogen into forms that plants can use, enriching soil fertility naturally and reducing the need for synthetic fertilizers. The squash spreads across the ground, creating living mulch that shades the soil. This shading suppresses weeds, reduces water evaporation, and moderates soil temperatures. Nutritionally, the system is equally remarkable. Corn provides carbohydrates, beans contribute protein and essential amino acids, and squash supplies vitamins and minerals. Together, they form a balanced diet. Modern applications. This approach could be adapted globally through intercropping systems. Large commercial farms could experiment with crop combinations tailored to local climates. Urban community gardens and school gardens could teach ecological relationships through Three Sisters plots. Farmers could reduce fertilizer inputs and improve resilience by increasing crop diversity. Modern precision agriculture technologies, including sensors and data analysis, could help optimize these polyculture systems at larger scales. Indigenous agroforestry systems. Agroforestry refers to integrating trees and shrubs into agricultural landscapes. Indigenous peoples across tropical and temperate regions have long practiced forms of agroforestry. In the Amazon basin, many indigenous communities manage forest gardens that contain dozens or even hundreds of useful species. Rather than clearing forests completely, they selectively cultivate fruit trees, medicinal plants, nuts, root crops, fibers, and other resources within forest ecosystems. These systems often resemble natural forests. Different plants occupy multiple vertical layers: tall canopy trees, smaller fruit trees, shrubs, vines, ground-level crops, root crops beneath the soil. This layered structure captures sunlight efficiently and provides habitat for birds, insects, mammals, and pollinators. Environmental benefits. Agroforestry systems can store substantial amounts of carbon in trees and soils, protect watersheds, reduce erosion, increase biodiversity, improve pollination, moderate local temperatures, provide multiple sources of food and income, integration into modern economies. Governments could provide incentives for farmers to establish agroforestry systems. Food companies could purchase products from shade-grown production systems. Agricultural extension programs could train producers in agroforestry design. Urban planners could establish edible forests in parks and public spaces. Rather than replacing all conventional agriculture, agroforestry could become an important component of diversified food systems. Terraced farming. Mountainous regions present unique agricultural challenges. Steep slopes increase erosion risk and make water management difficult. Indigenous peoples of the Andes developed intricate terrace systems, particularly during the era of the ancestors of the Inca. Terraces transform steep hillsides into a series of flat steps supported by retaining walls. These structures reduce the speed of water runoff and allow moisture to infiltrate soils gradually. Terraces also create microclimates. Differences in elevation and stone construction influence temperature and humidity. Farmers historically used these variations to cultivate diverse crops suited to different conditions. Contemporary relevance. Many regions currently experiencing severe erosion could restore terraces. Terrace rehabilitation could improve food security in mountain communities while reducing landslide risks. Combining traditional terrace design with modern engineering could increase durability and efficiency. As climate change intensifies rainfall extremes, terraces may become increasingly valuable tools for water management. Cultural burning and indigenous fire stewardship. Fire is often viewed exclusively as destructive. However, many indigenous peoples have long recognized fire as an ecological process that, when carefully managed, can maintain healthy landscapes. Indigenous communities in Australia and across North America historically conducted controlled, low-intensity burns under carefully selected conditions. These burns served many purposes. They reduced accumulated vegetation that could otherwise fuel catastrophic wildfires. They encouraged the growth of edible and medicinal plants. They improved habitat conditions for wildlife. They facilitated hunting and travel. They recycled nutrients into soils. Colonial policies in many countries oppressed indigenous burning practices. As a result, forests accumulated unusually large fuel loads. Scientists increasingly recognize that excluding fire from fire-adapted ecosystems has contributed to more severe wildfires. Integrating cultural burning today, governments could establish partnerships with indigenous fire practitioners. Fire management agencies could incorporate traditional seasonal knowledge into prescribed burning programs. Training initiatives could support indigenous leadership in wildfire prevention. Such collaborations are already emerging in parts of Australia, Canada, and the United States. Indigenous water management systems. Water scarcity has challenged societies throughout history. Indigenous communities develop sophisticated methods to capture, store, distribute, and conserve water. Examples include floodwater farming in arid landscapes, seasonal wetland cultivation, traditional irrigation canals, rainwater harvesting structures, small-scale water retention systems. These approaches often worked with natural hydrological cycles rather than imposing rigid control over them. Floodwaters were slowed and spread across landscapes. Seasonal variations were anticipated and incorporated into agricultural calendars. Modern significance. Climate change is increasing drought frequency in many regions. Indigenous water systems could inspire decentralized approaches to water management that complement modern infrastructure. Cities could adopt rain gardens and permeable landscapes. Farms could implement water harvesting earthworks. Watershed restoration projects could incorporate indigenous hydrological knowledge, indigenous seed stewardship, and biodiversity conservation. Another essential contribution involves the preservation of genetic diversity. Many indigenous farmers maintain numerous crop varieties adapted to local conditions. These varieties often differ in drought tolerance, pest resistance, taste, nutritional composition, and maturation time. Industrial agriculture tends to rely on relatively few high-yield varieties. Although productive, this can reduce resilience. Seed diversity functions as insurance against environmental uncertainty. Supporting indigenous seed networks could strengthen global food security by preserving valuable genetic resources needed to adapt agriculture to changing climates. Integrating indigenous knowledge with modern science. Integration should not involve replacing science with tradition or treating indigenous knowledge as folklore. Traditional ecological knowledge represents cumulative observations refined over generations. Modern science offers powerful analytical tools. Together they can complement each other. For example, satellite imagery can monitor forest health. Soil testing can quantify regenerative outcomes. Climate models can inform adaptation planning. Indigenous observations can identify ecological changes not captured by remote sensing. Geographic information systems can support community-led land management. Collaborative research involving indigenous communities as equal partners can generate innovative solutions. Policy reforms needed. Technical solutions alone are insufficient. Governments would need to reform institutions and incentives. Recognizing indigenous rights. Secure land tenure encourages long-term stewardship. Numerous studies indicate that indigenous managed territories often experience lower rates of deforestation than surrounding lands. Protecting indigenous rights includes recognizing land ownership and governance, respecting cultural practices, obtaining free, prior and informed consent, sharing benefits equitably, reforming subsidies. Many agricultural subsidies currently reward production volume rather than ecosystem outcomes. Policies could instead compensate producers for carbon sequestration, soil restoration, biodiversity conservation, water quality improvement, pollinator habitat creation, supporting indigenous leadership. Indigenous experts should participate in decision-making processes at local, national, and international levels. Programs should support indigenous-led education, restoration projects, and agricultural enterprises. Education and public awareness. Educational institutions can help bridge knowledge systems. Schools and universities could include indigenous ecological knowledge in curricula. Demonstration farms could showcase regenerative techniques. Extension programs could train producers in diversified farming methods. Public awareness campaigns could challenge misconceptions that traditional knowledge is outdated. Instead, indigenous innovations should be recognized as living systems that continue to evolve. Urban applications. Even highly urbanized societies can incorporate indigenous regenerative principles. Cities could establish community food forests, native plant corridors, pollinator gardens, composting initiatives, rainwater harvesting systems, edible school landscapes, green infrastructure that mimics natural ecosystems. These measures can improve public health, strengthen local food systems, reduce urban heat islands, and reconnect people with ecological processes. Challenges and ethical considerations. Integrating indigenous systems globally is not without challenges. Practices developed in one ecosystem cannot simply be transplanted elsewhere without adaptation. Cultural appropriation must be avoided. Indigenous communities should receive recognition, authority, and benefits arising from the use of their knowledge. Economic structures favoring industrial production may resist change. Transition periods can involve cost and uncertainty for producers. Nevertheless, these obstacles can be addressed through respectful collaboration, participatory research, and supportive public policy toward a regenerative future. The future of sustainable agriculture does not lie in returning entirely to the past or relying exclusively on industrial methods. Rather, it may emerge through a synthesis of indigenous ecological wisdom and modern scientific capabilities. Indigenous regenerative systems demonstrate that human societies can produce food, fiber, and medicine while restoring soils, conserving water, supporting biodiversity, and strengthening community resilience. By embracing diversity, long-term stewardship, and reciprocity with the natural world, modern societies can move toward agricultural systems that nourish both people and the ecosystems upon which all life depends. Building a city inspired by indigenous systems of sustainability and ecological harmony would require much more than adding parks or installing renewable energy technologies. It would involve fundamentally redesigning the relationship between people, communities, economies, and the natural systems that support life. Such a city would not attempt to dominate or separate itself from nature. Instead, it would function as a living ecosystem in which human activities contribute to the health of soils, waterways, forests, wildlife, and future generations. Because indigenous cultures are extraordinarily diverse, there is no single native city model. However, many indigenous societies shared broad principles that can guide urban design: reciprocity, stewardship, diversity, long-term thinking, adaptation to local ecosystems, community responsibility, and respect for ecological limits. Combining these principles with modern science, engineering, and technology could help create cities that are both highly livable and environmentally regenerative. Foundational philosophy: a city as a living ecosystem. Most modern cities operate according to a linear model. Resources enter, people consume, their waste leaves the city. Food is imported from distant regions, energy arrives from centralized systems, water is extracted and discharged elsewhere, and waste is transported to landfills. An indigenous-inspired city would instead function according to a circular ecological model. Ecosystems provide resources, communities use them responsibly, materials are reused, regenerated, and returned to support ecosystem health. The city would ask not only, how can we reduce harm, but also, how can the city actively improve the landscapes around it? The goal would be regeneration rather than mere sustainability. Governance based on future generations. At the heart of the city would be a governance system guided by long-term responsibility, inspired by concepts such as the seventh-generation principle associated with the Haudenosaunee Confederacy. City leaders would evaluate major decisions according to their impacts on people and ecosystems many decades into the future. Institutional structures might include a Future Generations Council composed of scientists, community members, youth representatives, and indigenous advisors. Mandatory environmental and social impact assessments spanning 50 to 100 years. Annual ecological accounting reports measuring ecosystem health alongside economic indicators. Citizen assemblies that encourage participatory decision-making. Success would be measured not only by economic growth but also by improvements in biodiversity, public health, social cohesion, and ecological resilience. Bioregional planning. Rather than imposing a universal urban blueprint, the city would be designed according to the characteristics of its specific region. Planners would study local climate patterns, native ecosystems, hydrological cycles, soil conditions, indigenous ecological knowledge, native plant and animal communities, Seasonal variations. A city in a desert environment would differ dramatically from one in a temperate forest or coastal wetland. This principle mirrors indigenous traditions of adapting lifestyles to local ecological realities instead of reshaping landscapes to fit standardized designs. Food production throughout the city. Modern cities generally separate food production from urban life. An indigenous-inspired city would reintegrate food systems into everyday environments. Food forests. Food forests mimic natural woodland ecosystems. They contain multiple layers, canopy trees, fruit and nut trees, shrubs, herbs, ground covers, vines, root crops. These systems provide food production, pollinator habitat, carbon sequestration, cooling through shade, recreational spaces, educational opportunities, community agriculture. Neighborhoods would include community gardens, school gardens, greenhouses, indigenous crop demonstration plots, shared orchards. Children and adults would gain practical experience growing food. Indigenous agricultural principles. Urban farms could incorporate polycultures rather than monocultures. Companion planting systems similar to the Three Sisters approach. Compost-based fertility. Seed-saving initiatives. Native edible plants. Food production would become a visible part of city life rather than a distant industrial process. Water as a sacred and living system. Many indigenous cultures regard water as a living relative deserving respect. Modern cities often channel rainwater into storm drains and rapidly remove it from urban areas. An indigenous-inspired city would instead treat water as a resource to be retained, purified, and celebrated. Features could include rain gardens that absorb runoff, bioswales integrated into streets, wetland restoration, permeable pavements, rainwater harvesting systems, constructed wetlands for wastewater treatment, stream daylighting projects, urban ponds supporting biodiversity. Water would move through the city slowly, replenishing groundwater and supporting ecosystems. Architecture inspired by place. Buildings would be designed according to regional conditions. Architectural principles would include passive environmental design. Structures would maximize natural ventilation, daylighting, thermal mass, seasonal shading, solar orientation, local materials. Where appropriate, construction could incorporate sustainably harvested timber, earth-based materials, bamboo, recycled materials, low-carbon alternatives. Cultural expression. Architecture would celebrate local identities and indigenous influences through collaborative design processes. Buildings would consume less energy while fostering a sense of belonging. Renewable and community energy systems. The city would transition from fossil fuel dependence toward renewable energy systems. These might include rooftop solar panels, community solar cooperatives, wind generation where appropriate, geothermal heating and cooling, battery storage, district energy systems, microgrids. Energy governance could involve community ownership models that distribute benefits more equitably. Efficiency and sufficiency would complement technological innovation. Circular economies and repair cultures. Many indigenous traditions emphasize careful use of resources. The city would therefore adopt circular economic principles. Systems could include repair cafes, tool libraries, materials recovery centers, reuse markets, product sharing platforms, community workshops, composting facilities. Products would be designed for durability and repair rather than disposal. Waste would increasingly become a resource. Mobility designed for human well-being. Transportation systems would prioritize people over automobiles. Features might include walkable neighborhoods, extensive cycling networks, electric public transit, mixed-use development, reduced commuting distances, accessible public spaces, green corridors connecting districts. Mobility would support community interaction and reduce pollution. Streets would become social and ecological spaces rather than primarily traffic corridors. Indigenous stewardship of biodiversity. The city would actively support non-human life. Urban ecosystems could include native plant corridors, pollinator gardens, bird habitats, wetland reserves, wildlife crossings, restored grasslands, community stewardship programs. Biodiversity would be recognized as essential infrastructure. Instead of isolating nature in small parks, ecological networks would permeate the entire city. Education embedded in daily life. Learning would extend beyond classrooms. Educational experiences would include outdoor education programs, ecological monitoring projects, intergenerational mentorship, indigenous knowledge exchanges, community restoration activities, food growing education, citizen science initiatives. Children would develop direct relationships with local ecosystems. Environmental literacy would become a core civic competency. Health and community. Indigenous perspectives often emphasize collective well-being. Neighborhood design could support shared gathering spaces, cultural centers, cooperative child care, accessible health care, recreational opportunities, community kitchens, social support networks. Health would be understood as emerging from relationships among people, communities, and environments. Disaster resilience. Climate change will expose cities to increasing risks. Drawing from indigenous adaptive traditions, resilience would emphasize diverse food systems, decentralized infrastructure, community preparedness networks, local knowledge, ecosystem restoration, redundant systems. Rather than relying solely on centralized responses, communities would possess the capacity to adapt and recover together. Economy of reciprocity. Perhaps the most transformative feature would be cultural. Modern urban economies often encourage continual consumption and competition. An indigenous-inspired city would cultivate reciprocity. Residents might ask, how much is enough? What responsibilities accompany prosperity? How can abundance be shared? How can today's actions benefit future generations? Economic success would include measures such as ecological restoration, reduced inequality, community participation, public health, cultural vitality, biodiversity recovery. A vision of the regenerative city. Imagine walking through such a city. You pass beneath fruit and nut trees growing along pedestrian streets. Rainwater flows through gardens filled with native plants rather than disappearing into concrete drains. Schools maintain food forests where students learn ecological science from teachers, elders, and community members. Neighborhood workshops repair appliances and bicycles instead of discarding them. Public buildings remain comfortable through passive design and renewable energy systems. Wetlands filter water while providing habitat for birds and pollinators. Citizens participate in decisions guided by concern for generations yet unborn. This city would not reject modern medicine, digital technologies, scientific research, advanced engineering, or renewable energy. Instead, it would place these achievements within a broader ethical framework rooted in stewardship, reciprocity, humility, and respect for the living systems that sustain human civilization. Such a city would represent neither a return to the past nor an idealized imitation of indigenous societies. It would be a new synthesis, a regenerative urban civilization in which indigenous wisdom and modern innovation work together to create places where both people and the rest of nature can flourish for generations to come. Building a regenerative city inspired by indigenous systems of sustainability, production, and ecological harmony. The majority of modern cities were designed during periods of industrial expansion, when the primary goals of urban planning were economic growth, industrial productivity, transportation efficiency, and population concentration. These objectives enabled unprecedented advances in wealth creation, technological innovation, healthcare, education, and communication. However, they also produced cities that often consume vast quantities of energy and materials while generating pollution, degrading ecosystems, fragmenting wildlife habitats, and disconnecting residents from the natural systems that sustain them. Many contemporary cities operate through what ecologists describe as a linear metabolism. Food, water, energy, construction materials, and consumer goods are extracted from distant places and transported into urban areas. Residents consume these resources, and the resulting waste is exported to landfills, incinerators, sewage systems, or polluted waterways. Cities become centers of consumption rather than participants in ecological cycles. Indigenous cultures throughout the world developed alternative ways of organizing human settlements. Although indigenous societies were highly diverse and adapted to different environments, many shared principles that encouraged long-term sustainability. These included reciprocity with nature, respect for ecological limits, stewardship of shared resources, adaptation to local ecosystems, intergenerational responsibility, community participation, and the recognition that human well-being depends upon healthy relationships among people and the more than human world. A city inspired by these principles would not attempt to recreate historical indigenous settlements exactly as they existed in the past. Modern urban populations are far larger, technological systems are more complex, and contemporary societies face challenges that previous generations could not have anticipated. Instead, the goal would be to synthesize indigenous ecological wisdom with modern science, engineering, public health, and democratic governance to create regenerative cities capable of supporting both human prosperity and ecological flourishing. Reimagining the city as a living ecosystem. One of the most profound transformations would involve changing how people conceptualize the city itself. In conventional planning, cities are often viewed as machines. Infrastructure is designed to maximize efficiency, transportation networks facilitate movement of people and goods, and natural systems are modified to accommodate development. A regenerative city would instead be understood as a living ecosystem. Just as forests cycle nutrients, wetlands purify water, and grasslands support diverse species interactions, cities could be designed to participate in ecological processes rather than interrupt them. This perspective recognizes that cities are not separate from nature. Human beings remain biological organisms dependent upon clean air, fertile soils, freshwater systems, stable climates, pollinators, biodiversity, and functioning ecosystems. Consequently, every component of the city would be evaluated according to questions such as, does this system regenerate or deplete ecological resources? Does it strengthen relationships among residents? Does it increase resilience for future generations? Does it contribute positively to ecosystem health? The objective would shift from minimizing environmental damage toward creating net positive relationships between urban life and the earth. Governance based on future generations. Many contemporary political systems prioritize short-term outcomes because elected officials often operate within election cycles lasting only a few years. As a result, decisions with significant long-term consequences may be shaped by immediate economic pressures. Many indigenous traditions, however, encourage decision-making guided by responsibility toward future generations. One of the most widely discussed examples is the principle associated with the seventh-generation philosophy of the Haudenosaunee Confederacy. According to this perspective, people should consider how present actions may affect descendants many generations into the future. Applying this principle within urban governance could fundamentally alter how cities make decisions. Institutional innovations might include future generations councils. Cities could establish advisory bodies composed of scientists, youth representatives, indigenous leaders, community members, and experts in ecology and public health. These councils would review major projects to assess their long-term implications. Extended impact assessments. Environmental assessments could examine consequences not merely over 5 or 10 years, but over periods spanning 50 to 100 years. Questions might include, will this development reduce biodiversity? Will it increase vulnerability to climate change? Will future residents inherit degraded infrastructure? Will it contribute to social inequality? Ecological accounting systems. Municipal performance could be evaluated using indicators such as soil health, water quality, tree canopy coverage, pollinator abundance, carbon sequestration, public health outcomes, access to green space. Economic prosperity would remain important, but it would be considered alongside ecological and social well-being. Bioregional planning, designing according to place. Many modern cities employ planning approaches that are remarkably similar regardless of climate or ecology. The same suburban layouts, building forms, and infrastructure systems appear in deserts, tropical regions, temperate forests, and coastal environments. Indigenous societies typically adapted their practices to local environmental conditions. A regenerative city would embrace this principle through bioregional planning. Bioregional planning begins by understanding the characteristics of the place itself. Planners would study watersheds, native ecosystems, local geology, seasonal weather patterns, indigenous ecological knowledge, historical disturbance regimes, wildlife migration routes, soil characteristics. These factors would shape urban design. For example, desert cities might emphasize water conservation, shaded pedestrian networks, and drought-resistant vegetation. Coastal cities might prioritize wetland restoration and flood-adaptive infrastructure. Forest cities could integrate extensive canopy systems and wildlife corridors. By designing with rather than against ecological realities, cities become more resilient and resource efficient. Integrating food production into urban life. One of the defining characteristics of industrial urbanism is the separation of consumers from food production. Food often travels thousands of miles before reaching city residents. This separation contributes to greenhouse gas emissions, weakens food security, and diminishes ecological awareness. Indigenous food systems frequently integrated production into community life. A regenerative city could restore these relationships. Urban food forests. Food forests are designed to mimic natural woodland ecosystems. Unlike conventional agriculture, which often relies on monocultures, food forests incorporate multiple layers of vegetation. These layers include tall canopy trees, fruit and nut trees, shrubs, herbaceous plants, ground covers, climbers and vines, root crops. Each layer performs ecological functions. Food forests provide fruits and nuts, wildlife habitat, pollinator resources, carbon storage, shade and cooling, stormwater absorption, educational opportunities. Residents would encounter food production in parks, school grounds, residential neighborhoods, and public spaces. Community agriculture. Neighborhoods could also include community gardens, shared orchards, greenhouses, seed libraries, indigenous crop demonstration plots, composting facilities. These initiatives strengthen food security while fostering social relationships. Water as a sacred and regenerative system. Many indigenous cultures regard water as a living entity deserving respect and care. Modern urban infrastructure often treats water as a commodity and storm water as a nuisance requiring rapid disposal. This approach contributes to flooding, pollution, groundwater depletion, and habitat destruction. A regenerative city would instead seek to slow, store, cleanse, and celebrate water. Rain gardens and bioswales. Vegetated depressions integrated into streetscapes capture runoff and allow water to infiltrate into soils. Plants absorb pollutants and reduce flood risks. Wetland restoration. Urban wetlands can filter contaminants, support biodiversity, and buffer communities against storms. Rainwater harvesting. Buildings could collect precipitation for non-potable uses such as irrigation and toilet flushing. Constructed wetlands. Wastewater treatment systems modeled after natural wetlands can remove nutrients and contaminants while providing habitat. Stream daylighting. Buried waterways could be restored to the surface, re-establishing ecological functions and reconnecting residents with local hydrology. Water would no longer disappear into hidden pipes. Instead, it would become a visible and valued participant in urban life. Architecture inspired by climate and ecology. Buildings account for substantial portions of global energy consumption. Traditional indigenous architecture often achieved comfort using passive strategies adapted to local climates. These approaches remain highly relevant. Passive design principles. Buildings could maximize natural ventilation, daylighting, seasonal solar gain, Thermal mass, cross breezes, strategic shading. Reducing dependence on mechanical systems lowers energy demand. Local and regenerative materials. Construction could prioritize sustainably harvested timber, earth-based materials, bamboo, recycled components, low-carbon concrete alternatives. Cultural identity. Architecture would emerge through collaboration with local communities and indigenous knowledge holders. Buildings would express regional identity while fostering belonging and continuity. Renewable energy and community ownership. Transitioning away from fossil fuels is essential for climate stability. However, indigenous principles suggest that the organization of energy systems also matters. Rather than concentrating ownership, regenerative cities could emphasize community participation. Examples include community solar cooperatives, neighborhood microgrids, shared battery storage, geothermal district systems, wind energy partnerships, peer-to-peer energy exchange. These arrangements distribute benefits more equitably and enhance resilience during disruptions. Efficiency and conservation would complement renewable generation, circular economies and resource stewardship. Many indigenous societies develop practices emphasizing careful use of materials, repair, reuse, and maintenance reflected respect for the labor and ecological relationships required to obtain resources. Modern economies frequently encourage disposability. A regenerative city would adopt circular principles. Components could include repair cafes, residents repair appliances, clothing, and electronics with community assistance. Tool libraries. People borrow infrequently used equipment instead of purchasing duplicates. Materials recovery centers. Valuable materials are recovered and reintroduced into production cycles. Reuse marketplaces. Furniture, construction materials, and household goods are exchanged and repurposed. Waste would increasingly become a design failure rather than an accepted outcome. Transportation designed for human flourishing. Many cities prioritize automobile movement above all else. This contributes to air pollution, greenhouse gas emissions, noise, traffic injuries, and social isolation. A regenerative city would redesign mobility around human well-being. Walkable neighborhoods. Daily necessities would be located within accessible distances. Cycling infrastructure. Protected networks encourage active transportation. Public transit, electric buses, trams, and rail systems provide equitable mobility. Mixed-use development, housing, employment, education, and recreation coexist within neighborhoods. Green corridors, transportation routes incorporate vegetation and ecological connectivity. Streets become places for social interaction rather than merely conduits for vehicles. Biodiversity as essential infrastructure. Nature in many cities is confined to isolated parks. Indigenous stewardship traditions demonstrate that humans can actively maintain habitats supporting diverse species. A regenerative city would treat biodiversity as essential infrastructure. Native vegetation would permeate urban landscapes. Ecological networks might include pollinator pathways, bird habitats, wetlands, native grasslands, wildlife crossings, riparian corridors, community stewardship programs. These systems provide ecosystem services such as pollination, temperature regulation, pest control, and psychological well-being. Cities would become refuges for both people and wildlife. Education embedded in everyday experience. Learning would extend beyond classrooms and standardized testing. Inspired by indigenous educational traditions, ecological literacy would develop through participation and observation. Students might monitor stream health, maintain gardens, restore habitats, learn from elders, conduct citizen science projects, participate in community planning. Knowledge becomes experiential and relational. Residents understand not only environmental concepts but also their responsibilities within ecological systems. Health, community, and social cohesion. Many indigenous worldviews recognize that health encompasses relationships among individuals, communities, and environments. Urban design could strengthen these relationships. Neighborhoods might include gathering spaces, community kitchens, cooperative child care facilities, cultural centers, accessible healthcare services, recreational areas, spaces for ceremonies and celebrations. Social cohesion reduces isolation and increases resilience during crises. Communities become capable of supporting one another. Disaster resilience through diversity. Climate change is increasing the frequency and intensity of disasters. Indigenous communities have long navigated environmental variability through adaptive strategies emphasizing diversity and cooperation. Regenerative cities could strengthen resilience by developing diverse food sources, distributed energy systems, local emergency networks, ecosystem-based flood protection, community preparedness programs, redundant infrastructure. Resilience emerges not from eliminating uncertainty but from increasing the capacity to adapt. Reciprocity as the city's ethical foundation. Perhaps the most transformative aspect of an indigenous-inspired city would be ethical rather than technological. Modern urban societies often encourage people to ask, how can we maximize convenience, growth, and consumption? A regenerative city would encourage different questions. What do we owe future generations? How can we give back to the ecosystems that sustain us? What constitutes enough? How can abundance be shared fairly? How can prosperity strengthen rather than diminish the living world? Reciprocity recognizes that every meal, every glass of water, every building material, and every breath depends upon relationships with ecosystems. Because we receive these gifts, we also inherit responsibilities toward the regenerative city of the future. A city inspired by indigenous systems would not reject scientific research, digital technologies, modern medicine, renewable energy, or advanced engineering. Instead, it would guide these innovations through principles refined by centuries of close relationships with local environments. Imagine walking through such a city. Streams flow openly through neighborhoods bordered by wetlands and native vegetation. Children harvest vegetables from school gardens and learn ecological knowledge from teachers, scientists, and elders. Fruit trees line pedestrian streets. Public buildings remain comfortable through passive design and renewable energy. Wildlife corridors connect parks across the urban landscape. Community workshops repair and repurpose materials. Residents participate in governance that considers the well-being of generations yet unborn. This vision does not represent a return to an idealized past. Rather, it represents a new synthesis, an urban civilization in which indigenous wisdom and contemporary innovation work together to create communities that are prosperous, resilient, equitable, and ecologically regenerative. Such cities would not merely strive to reduce their environmental footprints. They would actively contribute to the flourishing of the people, ecosystems, and future generations that depend upon them. It is important to recognize that there is no single indigenous city model. Indigenous peoples represent thousands of distinct cultures that have inhabited deserts, forests, grasslands, mountains, wetlands, islands, and Arctic environments. Their social systems, technologies, spiritual traditions, and relationships with the land have been extraordinarily diverse. Nevertheless, many indigenous societies develop principles of stewardship, reciprocity, adaptation, collective responsibility, and ecological awareness that enabled communities to thrive within the ecological limits of their environments for generations. The following essay explores how these principles, combined with modern science and technology, could inspire the creation of a regenerative city designed for the 21st century and beyond. Building the regenerative city, designing urban civilization through indigenous principles of sustainability and ecological harmony. Humanity has become an urban species. More than half of the world's population now lives in cities, and that proportion is expected to continue increasing throughout the 21st century. Cities are centers of innovation, culture, education, commerce, and political power. They have generated remarkable achievements in medicine, science, art, and technology. At the same time, they are responsible for a large share of global resource consumption, greenhouse gas emissions, waste production, and ecological degradation. Many modern cities depend upon vast networks of extraction that draw food, water, energy, timber, minerals, and labor from distant regions while exporting pollution and waste beyond their boundaries. The environmental crises confronting humanity, including climate change, biodiversity loss, freshwater depletion, pollution, and soil degradation, suggest that the prevailing model of urban development is no longer sufficient. Although technological advances such as renewable energy, efficient transportation systems, and smart infrastructure are essential, technology alone cannot resolve the deeper questions concerning humanity's relationship with the living world. To build truly sustainable cities, societies may need to rethink the philosophical foundations upon which urban civilization is based. Indigenous cultures throughout the world offer valuable insights for this transformation. Although indigenous societies differ enormously in their histories, environments, and traditions, many developed systems that allowed communities to flourish while maintaining the ecological integrity of the landscapes upon which they depended. Their approaches often emphasized reciprocity, stewardship, intergenerational responsibility, adaptation to place, collective well-being, and respect for ecological limits. These principles emerged through centuries or even millennia of close observation and participation within local ecosystems. A regenerative city inspired by indigenous wisdom would not seek to recreate historical settlements exactly as they once existed. Modern urban populations, technologies, and institutions are fundamentally different from those of the past. Instead, such a city would represent a creative synthesis in which indigenous ecological principles guide contemporary scientific innovation, engineering, architecture, governance, and economic life. The objective would not simply be to reduce environmental harm, but to create cities that actively regenerate ecological systems while supporting human flourishing. One of the most fundamental transformations would involve changing how people understand the city itself. Conventional urban planning often treats cities as machines designed to maximize efficiency, economic productivity, and growth. Infrastructure systems transport resources into cities, distribute them among residents, and remove waste as quickly as possible. This linear model mirrors industrial production processes in which materials are extracted, consumed, and discarded. A regenerative city would instead be understood as a living ecosystem. Just as forests cycle nutrients, wetlands cleanse water, and grasslands support diverse interactions among species, cities could be designed to participate in ecological processes rather than disrupt them. Human settlements would become components of larger ecological networks rather than isolated spaces separated from nature. This ecological perspective recognizes recognizes that human prosperity depends upon healthy relationships with the systems that sustain life. Clean water, fertile soils, pollinators, stable climates, biodiversity, and functioning ecosystems are not luxuries external to urban existence. They constitute the biological foundation upon which civilization itself depends. Governance within such a city would also undergo profound transformation. Contemporary political systems often encourage short-term decision-making because elected officials operate within limited electoral cycles. Immediate economic concerns frequently overshadow long-term ecological considerations. Indigenous traditions, however, frequently emphasize responsibility toward future generations. One influential example is the seventh-generation philosophy associated with the Haudenosaunee Confederacy. Although interpretations vary, the principle encourages people to consider how present actions may affect descendants many generations into the future. Applying this perspective to urban governance would require institutions capable of extending society's time horizon beyond immediate political and economic pressures. Future generations councils could be established to evaluate major policy decisions according to their long-term consequences. These councils might include scientists, indigenous representatives, youth delegates, public health experts, and community members. Major infrastructure projects would undergo assessments examining their potential impacts over 50 or 100 years, rather than merely a decade. Municipal success could be measured through ecological accounting systems that track biodiversity, water quality, soil health, tree canopy coverage, public health, and social equity alongside economic indicators. Another defining feature of the regenerative city would be its commitment to bioregional planning. Modern urban design often imposes similar development patterns across vastly different ecological contexts. Suburban subdivisions, road networks, and architectural styles appear in deserts, tropical regions, coastal environments, and temperate forests despite profound environmental differences. Indigenous societies generally adapted their practices to local conditions. Housing designs reflected climate, agricultural systems matched soils and rainfall patterns, and resource management strategies evolved in response to ecosystem dynamics. A regenerative city would embrace this principle by designing according to place. Urban planners would begin by studying watersheds, native ecosystems, wildlife migration routes, geological conditions, historical disturbance patterns, and indigenous ecological knowledge. Desert cities would prioritize water conservation, shade, and drought-tolerant vegetation. Coastal cities would restore wetlands and accommodate flooding. Forest cities would preserve canopy systems and ecological connectivity. Urban form would emerge from the characteristics of the landscape, rather than forcing landscapes to conform to standardized templates. Food systems would likewise be transformed. One of the defining characteristics of industrial urbanism is the separation of food production from everyday life. Most urban residents rarely encounter the landscapes and labor responsible for producing their meals. Food travels long distances through complex supply chains before arriving at grocery stores and restaurants. Indigenous food systems frequently integrated production into community life. A regenerative city could restore this relationship by embedding agriculture throughout the urban fabric. Community gardens, shared orchards, rooftop greenhouses, seed libraries, and school gardens would become common features of neighborhoods. Food forests designed to mimic natural ecosystems could provide fruits, nuts, herbs, and medicinal plants while simultaneously supporting pollinators, cooling neighborhoods, sequestering carbon, and managing storm water. These food systems would emphasize diversity rather than monoculture. Indigenous agricultural principles such as companion planting, seed stewardship, and polyculture could increase resilience while strengthening food security. Residents would gain opportunities to participate directly in food production, fostering ecological awareness and community engagement. Water management would reflect a similarly profound shift in values. Many indigenous cultures understand water not merely as a resource, but as a living presence deserving respect and care. Modern cities often treat stormwater as waste requiring rapid disposal through underground drainage systems. This approach contributes to flooding, groundwater depletion, pollution, and habitat destruction. A regenerative city would seek to slow, store, cleanse, and celebrate water. Rain gardens, bioswales, permeable pavements, restored wetlands, rainwater harvesting systems, and constructed wetlands for wastewater treatment would become integral elements of urban infrastructure. Buried streams could be restored to the surface through daylighting projects, reconnecting residents with local hydrological systems. Water would no longer disappear into hidden pipes. Instead, it would become visible within parks, streetscapes, and public spaces, reminding residents of their dependence upon healthy watersheds and encouraging stewardship. Architecture would also reflect indigenous principles of adaptation and ecological intelligence. Traditional indigenous structures often achieved thermal comfort using passive strategies suited to local climates. Thick earthen walls moderated temperature fluctuations in arid environments, while elevated buildings promoted ventilation and reduced flood risks in humid regions. Modern architecture can build upon these insights through climate-responsive design. Buildings could maximize natural ventilation, daylighting, seasonal solar gain, shading, and thermal mass. Construction materials might prioritize sustainably harvested timber, recycled components, earth-based materials, bamboo, and low-carbon alternatives. Rather than pursuing a universal aesthetic, architecture would celebrate regional identity and cultural diversity. Energy systems would transition away from fossil fuels toward renewable and community-centered models. Solar panels, wind turbines, geothermal systems, and battery storage would reduce greenhouse gas emissions. Yet indigenous principles suggest that the organization of energy systems matters as much as the technologies themselves. Community-owned solar cooperatives, neighborhood microgrids, and shared energy systems could distribute benefits more equitably while increasing resilience during disruptions. Conservation and sufficiency would complement efficiency, recognizing that sustainability involves both technological innovation and cultural values concerning consumption. Economic systems would also be redesigned. Many indigenous societies emphasize reciprocity, sharing, and responsible use of resources. Objects were repaired, reused, and maintained because obtaining materials required labor, skill, and ecological relationships. A regenerative city could embody these values through circular economies. Repair cafes, tool libraries, reuse marketplaces, materials recovery facilities, and community workshops would extend product lifespans and reduce waste. Durable design standards and right-to-repair policies could discourage planned obsolescence. Waste itself would increasingly be viewed as evidence of poor design rather than an inevitable consequence of prosperity. Transportation systems would prioritize human well-being rather than automobile dominance. Walkable neighborhoods, protected cycling infrastructure, electric public transit, and mixed-use development would reduce emissions while strengthening social interaction. Green corridors integrated into transportation networks would support biodiversity and provide pleasant public spaces. Nature would not be confined to isolated parks. Biodiversity would become essential urban infrastructure. Native vegetation, pollinator pathways, wetlands, grasslands, wildlife crossings, and riparian corridors would permeate the city. Residents would encounter birds, butterflies, native plants, and functioning ecosystems throughout daily life. Education would similarly extend beyond classroom walls. Indigenous educational traditions frequently emphasize experiential learning, mentorship, observation, and participation. Students in regenerative cities might monitor stream health, restore habitats, maintain gardens, and collaborate with elders, scientists, and community organizations. Ecological literacy would become a fundamental civic competency. Health would be understood holistically. Many indigenous perspectives recognize that well-being emerges through relationships among individuals, communities, and environments. Access to healthcare would remain essential, but urban design would also support mental health, social cohesion, physical activity, cultural expression, and connection to nature. Gathering spaces, community kitchens, cultural centers, and recreational opportunities would strengthen relationships and reduce isolation. As climate change intensifies environmental uncertainty, resilience would become increasingly important. Indigenous communities have long navigated disturbances such as droughts, floods, storms, and resource fluctuations through strategies emphasizing diversity, flexibility, and cooperation. Regenerative cities could adopt similar principles by diversifying food sources, decentralizing infrastructure, restoring ecosystems, and cultivating strong community networks capable of mutual support during crises. Ultimately, however, the most transformative contribution indigenous traditions may offer is ethical rather than technical. Many indigenous worldviews emphasize reciprocity, the understanding that human beings continuously receive gifts from the natural world and therefore carry responsibilities in return. Every meal, every drink of water, every building material, and every breath depends upon relationships with living systems. Prosperity therefore entails obligations to future generations, neighboring communities, and the ecosystems that sustain life. Modern societies often define success through continuous economic growth and increasing consumption. A regenerative city inspired by indigenous principles would ask different questions. How much is enough? What responsibilities accompany abundance? How can communities give back to the landscapes that support them? How can development contribute positively to the flourishing of both human and non-human life? The answers to these questions may shape the future of urban civilization. A city inspired by indigenous systems of sustainability would not reject scientific knowledge, modern medicine, renewable energy technologies, or advanced engineering. Rather, it would guide these innovations through principles refined over centuries of close relationships with place. Such a city would not merely seek to minimize its ecological footprint. It would strive to heal watersheds, restore biodiversity, regenerate soils, strengthen communities, and cultivate a culture of reciprocity and care. In this vision, the city becomes more than a center of consumption and production. It becomes a participant in the living world, a place where people, ecosystems, and future generations can thrive together. The challenge of the 21st century is not simply to build smarter cities, it is to build wiser ones. Indigenous wisdom, combined with contemporary knowledge and creativity, may provide some of the guidance humanity needs to meet that challenge. This presents one possible vision of a regenerative urban future, not a return to the past, but a synthesis of indigenous ecological wisdom and modern innovation aimed at creating cities that are resilient, equitable, prosperous, and capable of enhancing the health of the earth rather than diminishing it. How can we integrate native peoples' variety of regenerative agriculture systems into modern society to increase sustainability and environmental friendliness globally? This is one of the most important and most overlooked questions in the entire sustainability conversation, because indigenous and native peoples have collectively developed, refined, and sustained agricultural and land management systems over thousands of years that modern science is only beginning to understand in their full sophistication. Integrating these systems into modern society is not charity toward indigenous communities. It is one of the most intelligent things a civilization preparing for long-term sustainability, and ultimately for the terraforming of other worlds, can do. The foundational principle, what indigenous agricultural knowledge actually is. Before any integration can be meaningful, modern society must fundamentally reframe how it understands indigenous agricultural knowledge. The dominant modern framing, that indigenous practices are primitive precursors to scientific agriculture, interesting as cultural artifacts but superseded by modern methods, is not just wrong. It is catastrophically wrong, and the consequences of acting on it are visible in the degraded soils, depleted aquifers, collapsing biodiversity, and destabilized climates that industrial agriculture has produced in a matter of decades. Indigenous agricultural systems are the product of thousands of years of systematic observation, experimentation, adaptation, and refinement, conducted by communities whose survival depended on getting the results right. They encode knowledge about local soils, microclimates, water systems, plant genetics, pest ecology, and seasonal cycles that no modern scientific institution has replicated, and in many cases has not even attempted to study. They are not approximations of scientific knowledge. They are a different and in many respects more sophisticated form of it, one optimized for long-term sustainability rather than short-term yield maximization. The integration challenge is therefore not how to take indigenous practices and fit them into modern agricultural science. It is how to create genuine partnerships between indigenous knowledge systems and modern science, partnerships in which each learns from the other, in which indigenous communities retain sovereignty over their knowledge and their land, and in which the insights of thousands of years of ecological relationship are allowed to enrich and correct the relatively brief and often destructive experiment of industrial agriculture. The major systems and their modern integration. The Three Sisters and polyculture systems. The system itself. The Three Sisters, corn, beans, and squash, cultivated together by numerous indigenous nations across North and Central America, represents one of the most elegant agricultural systems ever devised. The three crops are not simply planted together for convenience. They are integrated in a relationship of mutual benefit that modern ecology recognizes as a sophisticated application of polyculture, nitrogen cycling, and microclimate management. Corn provides a vertical structure on which beans climb, freeing the beans from the need to invest in their own structural support and allowing them to concentrate resources on seed production. Beans fix atmospheric nitrogen through their root symbiosis with rhizobium bacteria, enriching the soil with the nutrient that corn, a notoriously nitrogen-hungry crop, demands in abundance. Squash spreads its large leaves across the soil surface, creating a living mulch that suppresses weeds, retains soil moisture, moderates soil temperature, and reduces erosion. The spiny texture of squash leaves and stems also deters pests and foragers. Together, the three crops produce a nutritionally complete diet. Corn provides carbohydrates, beans provide protein and complementary amino acids. Squash provides vitamins and minerals from a single planting that builds rather than depletes soil fertility, manages water efficiently, and requires minimal external inputs. Modern integration. Integrating Three Sisters polyculture into modern agriculture requires confronting the fundamental incompatibility between indigenous polyculture design and industrial monoculture infrastructure. Modern planting, cultivation, and harvesting machinery is designed for single-species rows. Applying it to mixed plantings requires either new machinery design or a shift towards smaller-scale, more labor-intensive production systems. The most practical integration pathway for large-scale agriculture is the development of companion planting systems inspired by Three Sisters principles, but adapted for mechanized production, legume intercrops that can be planted and harvested. With modified equipment, cover crop mixtures that provide soil benefits between cash crop seasons, and strip cropping systems that alternate nitrogen-fixing and nitrogen-demanding crops in patterns compatible with existing machinery. For smaller scale, community, and urban agriculture, direct adoption of Three Sisters and related polyculture systems is immediately practical. Community-supported agriculture operations, school gardens, urban farms, and smallholder operations worldwide are already adopting polyculture approaches, and finding that they produce more food per unit of land, require fewer fewer purchased inputs, and build soil health in ways that monocultures cannot. Agricultural research institutions must invest in studying polyculture systems, understanding the ecological mechanisms that make them productive, developing optimized variety combinations for different climates and soils, and designing appropriate equipment and management systems. This research must be conducted in genuine partnership with indigenous communities who hold deep knowledge of these systems, with benefit-sharing agreements that ensure indigenous communities gain from the commercialization of their knowledge. Milpa system. The system itself. The Milpa system of Mesoamerica extends the Three Sisters concept into a sophisticated long-rotation land management system. In traditional Milpa practice, a plot of forest is cleared, using fire to return nutrients to the soil in ash, cultivated for 2 to 3 years with rotating polycultures, then allowed to revert to forest for 10 to 20 years while a new plot is cleared and cultivated. This rotation system is not, as it was long described by colonial agronomists, primitive/and-burn agriculture reflecting a lack of knowledge about permanent cultivation. It is a sophisticated management of the forest-agriculture interface that mimics natural disturbance regimes, maintains soil fertility through forest regrowth and organic matter accumulation, preserves biodiversity in the forest fallow periods, and produces yield sustainable over millennia without external inputs. Modern research has confirmed that Milpa fallow forests accumulate soil organic matter, fix nitrogen, harbor beneficial mycorrhizal networks, support pollinator populations, and maintain the microbial soil communities that make subsequent cultivation productive, all without any manufactured inputs. The system is, in essence, a solar-powered soil renewal engine. Modern integration. The integration of Milpa principles into modern agriculture and land management addresses one of the most serious failures of industrial agriculture, the treatment of soil as an inert growth medium rather than a living system that requires renewal. At the farm scale, rotational fallow systems, incorporating trees, shrubs, and diverse herbaceous cover into crop rotations, apply the core Milpa insight to agricultural landscapes. Agroforestry systems that rotate crops with tree cover, silvopastoral systems that integrate trees with pasture, and cover crop rotations that include diverse mixes of legumes and grasses, all embody variations of the Milpa principle of allowing biological processes to renew soil fertility between cropping periods. At the landscape scale, Milpa principles suggest a fundamental redesign of agricultural landscapes, from vast monoculture expanses to mosaics of cultivated plots in recovering forest or shrubland, managed as dynamic systems in which the boundaries shift over time. This landscape mosaic approach has been shown to dramatically increase biodiversity, water quality, and ecosystem service provision compared to either intensive monoculture or complete forest protection. Policy integration requires reforming agricultural subsidy systems that currently reward continuous cropping, penalizing farmers economically for the fallow periods that regenerate their soil, and replacing them with systems that reward soil health outcomes, biodiversity, and long-term productivity. Andean terrace systems, Weru and Andines. The system itself. The agricultural engineering of the Andean civilizations, particularly the Inca and their predecessors, represents one of the most sophisticated landscape modification systems in human history. The Andean highlands present extreme agricultural challenges, steep slopes subject to erosion, wide temperature swings between day and night, frost risk even at low latitudes due to altitude, and irregular rainfall. The indigenous response was the development of two complementary systems, Andines, stonewalled terraces that convert steep slopes into level growing surfaces, and Weru, raised field systems in seasonally flooded lake basins. Andines terraces are not simply erosion control structures. They are microclimate engineering systems. The stone walls absorb heat during the day and release it slowly at night, raising minimum temperatures in the field immediately adjacent to the wall by several degrees, enough to prevent frost damage in regions where frost would otherwise make cultivation impossible. The terraces also intercept and redirect water, preventing runoff while allowing deep soil moisture storage. Their orientation is carefully chosen to maximize solar exposure. The soil in mature Andean terraces, built up over centuries of organic matter addition and biological activity, is dramatically more fertile than the surrounding hillside soils. Weru raised fields in the Bolivian and Peruvian Altiplano around Lake Titicaca are equally sophisticated. Raised planting platforms are separated by water channels. The water channels absorb solar heat during the day and release it at night, creating a thermal buffer that protects crops from the severe frost of the Altiplano, which can occur on any night of the year. The channels also support aquatic plants and animals that provide organic matter, and the sediment from the channels, periodically cleaned out and spread on the raised beds, provides nutrients. When Spanish colonization disrupted these systems, agricultural productivity in the Andes collapsed catastrophically. When Peruvian and Bolivian researchers, working with local indigenous communities, began rehabilitating Weru in the 1980s, agricultural yields on restored raised fields exceeded those of adjacent modern agriculture by factors of 2 to 3, without any chemical inputs. Modern integration. The integration of Andean terrace and raised field systems into modern agriculture has multiple dimensions. For hillside agriculture globally, representing a significant fraction of world food production and a disproportionate fraction of soil erosion, Andenes principles offer a template for terrace design that goes far beyond simple erosion control. Modern terrace design incorporating thermal mass, microclimate management, soil building, and water harvesting can dramatically improve productivity and resilience on sloped agricultural land worldwide. In frost-prone high-altitude regions, not just in the Andes but in mountain agricultural systems across Asia, Africa, and the Americas, the thermal buffering principles of Weru offer an entirely natural frost protection system that requires no energy input. Water channels and raised beds designed on Weru principles can extend the frost-free growing season, enable cultivation at higher altitudes, and protect crops during cold snaps, replacing expensive plastic mulches, wind machines, or irrigation-based frost protection systems. For climate adaptation globally, the Andean systems offer particular relevance. As climate change increases the frequency of temperature extremes and disrupts rainfall patterns, the microclimate engineering and water management sophistication of these ancient systems becomes increasingly valuable. Modern civil engineering and landscape architecture have much to learn from the engineering principles embedded in these systems. Indigenous forest management, cultural burning and forest gardens. Cultural burning, indigenous fire management, practiced by Aboriginal Australians, Native American nations, and indigenous peoples on every vegetated continent, is one of the most consequential and most thoroughly misunderstood land management systems in human history. Aboriginal Australians developed a system of cultural burning, sometimes called fire stick farming, over at least 50,000 years of continuous practice. Small, low-intensity fires were set at carefully chosen times and places to achieve specific land management outcomes, clearing undergrowth to facilitate travel and hunting, promoting the growth of food plants, creating habitat mosaics that support diverse wildlife, preventing the accumulation of fuel loads that would produce catastrophic wildfires, and managing the landscape to maintain the particular mosaic of vegetation communities that supported Aboriginal life. The suppression of cultural burning by colonial governments, based on the belief that fire was always destructive, has had catastrophic consequences across Australia, California, and many other regions. Without regular low-intensity burning, fuel loads accumulated over decades until they supported the kind of catastrophic megafires that have devastated Australia, California, the Amazon, and Siberia with increasing frequency and severity. The fires of the 2019 to 2020 Australian season, which burned more than 18 million hectares, were in large part the result of a century of fire suppression that had ended the land management system that prevented such catastrophes. The reintegration of cultural burning into modern land management, underway in Australia, California, and elsewhere, led by Indigenous fire practitioners working alongside government land managers, is one of the most important environmental policy developments of recent decades. Modern integration means returning legal authority to Indigenous fire practitioners to conduct cultural burns on country, investing in the intergenerational transmission of fire knowledge within Indigenous communities, training government fire managers in cultural burning principles, reforming liability laws that currently expose landowners and land managers to legal risk from prescribed burns, and incorporating cultural burning into national fire management plans as a primary tool rather than an afterthought. Indigenous forest gardens. The forest gardens of the Pacific Northwest, particularly those of the Coast Salish and other First Nations peoples, are another example of sophisticated land management that blurs the boundary between cultivation and wilderness. These are not cleared agricultural fields but managed forest ecosystems in which human intervention, planting, pruning, selective harvesting, burning, transplanting, over generations has shaped the species composition, structure, and productivity of what appears to outsiders as natural forest. Pacific Northwest forest gardens have high densities of food-producing trees and shrubs, camas, wapato, berry plants, fruit and nut trees, interspersed with other forest species in a structure that mimics natural forest, while being dramatically more productive of human food than unmanaged forest. The management history is encoded in the landscape, unusual species distributions, abnormally dense stands of food plants, evidence of historical clearing and planting, that researchers are only now learning to read. The integration of forest garden principles into modern land use represents a profound alternative to the binary of agriculture versus wilderness. Food forests, multi-story plantings of fruit and nut trees, berry shrubs, herbaceous food plants, and ground covers that together mimic forest structure while producing food, are the modern expression of this principle, applicable in temperate and tropical regions worldwide. Water management systems. Canid and aqueduct systems. Indigenous water management systems across arid and semi-arid regions represent engineering achievements of extraordinary sophistication. The Canid system of the Middle East and Central Asia, a network of underground channels that taps into mountain aquifers and delivers water by gravity to lowland agricultural areas, has sustained agriculture in some of the world's most arid environments for thousands of years. The key innovation is that water travels underground to the point of use, preventing the enormous evaporative losses that plague surface canal systems in hot, dry climates. Thousands of Canid systems remain operational in Iran, Afghanistan, and neighboring countries, some thousands of years old. They represent a form of water infrastructure that is self-maintaining. The slight downward gradient that drives water flow also causes the channels to self-clean, requires no energy input, and is far more resilient to climate variability than modern pump-dependent irrigation systems. The Zuni waffle gardens of the American Southwest both represent a different but equally ingenious water management approach. Flat-bottomed garden plots surrounded by low earthen walls create a grid of shallow basins, the waffles, that capture and hold every drop of rainfall and irrigation water, preventing runoff and forcing deep soil infiltration. In an environment receiving 250 to 350 millimeters of annual rainfall, waffle garden design can more than double the amount of that rainfall that becomes available to crops. The integration of these systems into modern water management means applying their underlying principles: gravity-driven conveyance, underground transport to minimize evaporation, landscape-scale water harvesting, and field design that maximizes water retention, to the design of modern irrigation and water harvesting systems. In regions facing increasing water scarcity due to climate change, these ancient engineering principles offer solutions that modern water engineering has largely ignored. Amazonian water management. The raised field systems of the Amazon basin, now visible through LiDAR surveys that penetrate the forest canopy, reveal that pre-Columbian Amazonian civilizations managed enormous areas of seasonally flooded savanna through sophisticated networks of raised cultivated platforms, canals, fish weirs, and water control structures. These systems simultaneously managed flooding, created dry planting surfaces, managed fish as a protein source, and controlled water distribution across millions of hectares. The integration of these principles into the management of seasonally flooded landscapes, the Pantanal, the Sudanese Sud, the Mekong Delta, the Mississippi floodplain, offers alternatives to the destructive drainage and conversion that have characterized modern management of these systems. Raised field systems can produce food from seasonally flooded landscapes without draining them, maintaining their ecological functions while producing human nutrition. Terra preta, Amazonian dark earths. The system itself, terra preta, Portuguese for dark earth, is one of the most remarkable agricultural discoveries of the late 20th century. Distributed across the Amazon basin in patches ranging from less than a hectare to several hundred hectares, terra preta soils are dramatically different from the surrounding highly weathered, nutrient-poor oxysoils that cover most of the Amazon basin. They are deep, rich in organic matter, teeming with microbial life, and extraordinarily fertile, producing crops at 2 to 3 times the yields achievable on adjacent soils without any fertilizer input, and they have maintained this fertility for hundreds to thousands of years since their creation. Terra preta was created by pre-Columbian Amazonian peoples through the intentional incorporation of charcoal, bone, organic waste, and other materials into the soil over extended periods. The charcoal, now recognized as biochar, is the key to the longevity of the fertility enhancement. Unlike organic matter, which decomposes within years, biochar persists in soil for centuries to millennia. Its highly porous structure provides habitat for enormous microbial populations, absorbs and retains nutrients that would otherwise leach from tropical soils, and improves water retention. Once established, terra preta soils appear to regenerate themselves. The microbial communities they support actively build organic matter from atmospheric carbon and soil minerals, maintaining and even extending the dark earth beyond its original boundaries. The rediscovery of terra preta has triggered enormous scientific interest in biochar as a soil amendment and carbon sequestration tool. Research programs across the world are studying terra preta properties, attempting to understand the precise processes by which they were created and maintained, and developing modern biochar production and application systems inspired by indigenous Amazonian practice. Modern integration. The integration of terra preta principles into modern agriculture represents one of the highest value sustainability integrations available, simultaneously improving soil fertility, sequestering carbon, reducing fertilizer requirements, and improving water efficiency. Modern biochar production from agricultural waste, forestry residues, and municipal organic waste, using pyrolysis systems that capture the energy released by heating, produces a material that can be applied to soils globally to recreate terra preta effects. The carbon stored in biochar is extremely stable, much more so than the carbon in compost or mulch, making biochar application a genuine long-term carbon sequestration strategy as well as a soil improvement tool. Integration at scale requires agricultural research programs that develop biochar application protocols optimized for different soils and crops, agricultural extension programs that teach farmers how to produce and apply biochar, policy mechanisms, carbon credits for verified biochar carbon sequestration, subsidies for biochar production systems that make biochar economically attractive, and processing infrastructure that converts agricultural and urban organic waste into biochar at community and regional scale. Integrated pest management through indigenous knowledge, companion planting and botanical pest control. Indigenous agricultural systems worldwide have developed sophisticated approaches to pest management that rely on ecological knowledge rather than chemical pesticides, knowledge of which plant combinations deter pests through volatile chemical signals, which plants attract pest predators, which physical barriers and timing manipulations reduce pest pressure, and which plant extracts have pesticidal properties. The Three Sisters system already incorporates pest management through companion planting. The volatile compounds released by squash leaves deter certain insect pests. The structural diversity of the polyculture makes it harder for specialist pests to find and colonize their target plants. The habitat diversity supports populations of beneficial insects, predatory wasps, lacewings, ground beetles, that control pest populations. Indigenous botanical knowledge includes hundreds of plant-derived pesticides, repellents, and attractants, ring-based preparations used across South and Southeast Asia, pyrethrin from chrysanthemum species used in Africa and Asia, nicotine-based preparations, essential oil extracts from dozens of aromatic plants, and numerous others, that provide pest control without the ecological devastation and human health risks of synthetic chemical pesticides. Integration into modern IPM. Integrating indigenous pest management knowledge into modern integrated pest management requires ethnobotanical research programs that systematically document and study traditional plant-based pest management practices, agricultural research that tests these practices in controlled conditions and develops optimized protocols, regulatory systems that can evaluate traditional botanical pesticides without requiring the same expensive registration process as novel synthetic chemicals, and extension programs that make proven traditional practices accessible to farmers globally. The market for botanical and ecological pest management is growing rapidly as concerns about the ecological and health impacts of synthetic pesticides drive demand for alternatives. Indigenous botanical knowledge represents an untapped reservoir of solutions that modern IPM research has barely begun to explore. The integration framework, how integration must be done. The history of attempts to integrate indigenous knowledge into modern systems is filled with failures, many of them deeply harmful to indigenous communities. Knowledge has been extracted without consent, commercialized without benefit sharing, stripped of its cultural and ecological context in ways that made it ineffective or misleading, and used to justify continued marginalization of the communities that created it. Any genuine integration framework must be built on principles that prevent these failures from recurring: free, prior, and informed consent. No integration of indigenous knowledge into modern systems should proceed without the free, prior, and informed consent of the indigenous communities who hold that knowledge. FPIC, a principle enshrined in the UN Declaration on the Rights of Indigenous Peoples, means that communities have the right to say no, that consent must be given before research or implementation begins rather than after, and that communities must have complete information about how their knowledge will be used, by whom, and for what purpose. In practice, FPIC means that research institutions, agricultural businesses, and government agencies seeking to work with indigenous agricultural knowledge must establish genuine relationships with indigenous communities before any knowledge transfer occurs, relationships built on trust, transparency, and mutual respect rather than extraction. Intellectual property and benefit sharing. Indigenous agricultural knowledge, including the genetic resources of the plant varieties that indigenous peoples have developed and maintained, is intellectual property that belongs to the communities who created it. The commercialization of this knowledge without benefit sharing is theft, and it has occurred repeatedly throughout the history of colonial and post-colonial agricultural research. Integrating indigenous knowledge fairly requires legal frameworks, including the Nagoya Protocol on Access and Benefit Sharing, that establish clear rights over traditional knowledge and genetic resources, with mandatory benefit sharing when these are commercialized. It requires research and business models that build indigenous communities in as partners and beneficiaries, rather than as sources to be extracted, and it requires the active prosecution of biopiracy, the unauthorized commercialization of traditional knowledge, as a genuine legal and ethical violation. Land rights as foundation. The most fundamental precondition for integrating indigenous agricultural systems into modern society is ensuring that indigenous peoples have secure rights to the land on which these systems are practiced. Indigenous land tenure is under threat across the world, from deforestation in the Amazon, from mining and energy extraction in North America, Australia, and Africa, from agricultural expansion in Southeast Asia, and from conservation programs that exclude indigenous communities from their traditional territories in the name of wilderness protection. Land rights integration means supporting indigenous land claims through legal and political advocacy, reforming tenure systems that fail to recognize collective indigenous land rights, enforcing existing laws that protect indigenous territories, and creating financial mechanisms that make sustainable indigenous land management economically viable so that communities are not driven by economic necessity to accept destructive development on their lands. Without secure land rights, indigenous agricultural systems cannot be sustained, let alone integrated into broader society. The land is not merely where the practices occur, it is the context that gives them meaning, the source of the ecological knowledge encoded in them, and the home of the communities whose identity and well-being are inseparable from their relationship with it. Two-way knowledge exchange. Genuine integration is not a one-way transfer of indigenous knowledge to modern science. It is a two-way exchange in which modern science also shares its tools, methods, and findings with indigenous communities in ways that support indigenous-led land management and food sovereignty. Modern genomic tools can help indigenous communities characterize and protect the genetic diversity of their traditional crop varieties. Remote sensing and GIS tools can support indigenous land monitoring and territory management. Climate modeling can provide locally relevant projections that inform indigenous adaptation planning. Soil science can deepen understanding of the mechanisms behind practices that empirical tradition has shown to be effective. This two-way exchange respects indigenous knowledge systems on their own terms while offering the tools of modern science and genuine partnership, not as a replacement for indigenous knowledge but as a complement to it. Integrating into modern institutions. Agricultural research and extension. Agricultural research institutions, universities, national agricultural research services, international research centers, must fundamentally transform their relationship with indigenous agricultural knowledge. The current model, in which modern science is the arbiter of what counts as valid knowledge and indigenous practices are evaluated against modern scientific criteria, must be replaced by a model of genuine knowledge pluralism in which indigenous epistemologies are respected on their own terms. Practically, this means hiring indigenous researchers in senior scientific positions, not just as community liaisons, establishing indigenous-led research programs that set their own agendas based on community priorities, funding long-term collaborative research that builds genuine relationships rather than one-time extractive studies, reforming research ethics frameworks to require FPIC and benefit sharing as standard practice, publishing research in indigenous languages in accessible formats alongside academic journals, recognizing indigenous knowledge contributions in scientific authorship and citation, agricultural extension services, the systems that translate research into farm-level practice, must similarly be transformed to incorporate indigenous knowledge as a primary source alongside modern research. Extension agents trained in both modern agronomy and indigenous land management practices, working alongside indigenous knowledge holders rather than replacing them, can serve as bridges between knowledge systems in ways that benefit farmers across the spectrum from traditional to commercial. Food policy and agricultural subsidies. The integration of indigenous agricultural systems into modern food policy requires reforming the subsidy and support systems that currently make industrial monoculture economically dominant regardless of its ecological costs. Agricultural subsidies should be reformed to reward outcomes, soil organic matter increase, biodiversity on farmland, water quality improvement, carbon sequestration, rather than production volumes. Payment for ecosystem services schemes should compensate indigenous land managers for the ecological services their traditional practices provide, biodiversity conservation, carbon storage, watershed protection, fire management. Food labeling systems that communicate the sustainability and provenance of food production practices can create market signals that reward indigenous and regenerative production methods. Public food procurement, school meals, hospital food, government catering, can create significant demand for food produced using indigenous and regenerative methods, providing the market signal that incentivizes adoption at scale. Urban planning and design. The integration of indigenous agricultural knowledge into urban environments transforms cities from purely food-consuming spaces into food-producing landscapes inspired by indigenous food system principles. Urban food forest designed on indigenous forest garden principles, multi-story edible plantings that mimic forest structure while producing food, can be integrated into parks, street verges, institutional grounds, and community spaces. Three Sisters polyculture gardens in school and community settings simultaneously produce food, teach ecological principles, and create cultural connections for indigenous urban residents. Water harvesting features inspired by indigenous water management systems, swales, rain gardens, wattle gardens, manage urban storm water while creating productive growing spaces. Urban planning processes that incorporate indigenous land management perspectives, including consultation with the indigenous peoples on whose traditional territory cities are built, can produce urban landscapes that are more ecologically functional, more food productive, and more culturally connected to the living systems they inhabit. The terraforming connection. Why indigenous agricultural knowledge is indispensable for terraforming. Every thread of indigenous agricultural knowledge described in this essay connects directly to the challenge of terraforming, the challenge of establishing sustainable food production, ecological function, and human civilization in an alien environment. Polyculture and ecological integration, the core of Three Sisters, milpa, and forest garden systems, is the foundation of any self-sustaining planetary food production system. Monocultures, dependent on external inputs and vulnerable to pest and disease outbreaks, cannot be sustained in the isolated, resource-constrained context of a planetary habitat. The ecological intelligence embedded in indigenous polyculture systems, how to design planned communities that sustain themselves, build their own fertility, and resist disruption, is foundational knowledge for planetary agriculture. Soil building, the fundamental achievement of terra preta, regenerative rotation systems, and composting traditions worldwide, is the central biological challenge of terraforming. Building living soil from sterile mineral substrate on another planet requires the deepest possible understanding of how soil forms, what organisms drive its development, and how human management can accelerate the process. Indigenous soil-building knowledge, accumulated over millennia of direct observation and refinement, is an irreplaceable contribution to this understanding. Water management, the genius of canned systems, waffle gardens, raised fields, and terrace systems, addresses the water scarcity that will characterize any planetary settlement in its early phases. The principles of minimizing evaporation, harvesting every available drop, recycling water through biological systems, and designing field geometries that maximize water retention are universal principles applicable to any water-scarce environment, including a Martian surface with limited ice resources. Cultural burning and landscape management, the sophisticated fire ecology knowledge of indigenous peoples worldwide, addresses the challenge of managing vegetation and ecosystem processes in a way that prevents catastrophic disruption. On a terraformed planet, managing the development of biological systems, preventing runaway growth of certain species, maintaining the diversity and balance of pioneer ecological communities, managing fire risk as biomass accumulates, will require the same landscape-scale ecological intelligence that indigenous fire management embodies. Resilience and adaptation, perhaps the deepest quality of all indigenous agricultural systems, is the capacity to sustain food production and ecological health across extreme variability in climate, pests, political disruption, and social change. Systems that have fed communities for thousands of years across enormous environmental variability have proven their resilience in the most rigorous testing environment possible. Actual history. A civilization preparing for the extreme challenges of planetary settlement needs exactly this kind of proven, deep resilience in its food and ecological systems. The vision, what a truly integrated society looks like, a society that has genuinely integrated indigenous regenerative agricultural knowledge into its institutions, practices, and culture looks profoundly different from today's industrial agricultural civilization. It is a society in which farmers manage living soils teeming with microbial communities, rather than sterile growth media requiring constant chemical inputs, in which landscapes are mosaics of productive forest, polyculture cropland, and recovering natural vegetation rather than vast monoculture expanses, in which water is harvested, retained, and recycled through layered biological systems, rather than pumped from depleting aquifers and drained away through concrete channels, in which fire is a management tool wielded with ecological intelligence, rather than a catastrophe to be suppressed until it becomes uncontrollable, in which food production is embedded in ecological function rather than opposed to it. It is also a society in which indigenous peoples are recognized as the authors of knowledge systems that are saving the world, with their rights to land, self-determination, and intellectual property fully respected, their communities thriving and their knowledge systems actively transmitted to new generations, and their voices central to the governance of land, food, and environment at every scale. And it is a society that, having learned from the oldest and deepest agricultural knowledge on Earth, carries those lessons outward, into space, onto other worlds, across the cosmos, as part of the accumulated wisdom of a civilization that learned, just in time, how to be a good steward of the living world. The integration of indigenous agricultural knowledge into modern society is not a romantic gesture toward the past. It is the most practically intelligent thing a civilization with terraforming ambitions can do. The future of life in the cosmos is written, in significant part, in the agricultural wisdom of the peoples who have been its most faithful stewards on this world.